thing that people have looked at for thousands and thousands of years. But as Professor Schmidt found out, the universe is a much more dynamic place than we give it credit for.
When Albert Einstein was doing his theory of gravity said the universe should be in motion. He didn't know if it was getting bigger or getting smaller, but his universe should have been in motion. And yet he looked around and said, well, the astronomers tell me that the universe is pretty static. Now, there were hints. In 1916, a guy by the name of Vesto Slipher saw that all of the galaxies in the sky were moving away from the Milky Way. And so that was a real funny measurement back then, and actually was indicating the motion of the universe.
But how did Slipher know that the galaxies were moving away from us? Well, he saw that their light was redshifted. If an object is moving away from us, its light appears more red. If it's moving towards us, its light appears more blue. And virtually all of the galaxies Slipher looked at were redshifted.
But it took till Hubble in 1929 to put it all together. And he went out and he measured distances to the nearest galaxies. Now, Slipher knew that these galaxies were moving away. Hubble looked at the stars in them, and what he noticed was that the faster that the object was moving away from us, the fainter the stars were. Now, stars become fainter when they're further away. So he said, well, let's just assume all those stars are about the same.
Hubble relied on what's called a standard candle. A standard candle is an object in space that always gives off the same amount of light. But as that light spreads out through space, it becomes less intense. So by looking at the intensity of the light, you can determine how far away the candle is. So if I walk out through this field behind me, you'll be able to tell how far away I am by how bright the candlelight looks.
By seeing that the stars were fainter, he could infer that the galaxies were further away. So the idea that the further away an object was, the faster it was moving, he said that means the universe is expanding. And you can think of it as if you put little dots on a balloon, you blow the balloon up, every dot moves away from every other dot, and the further the two dots are away, the faster they're actually moving away from each other when you blow the balloon up. It's just like the expanding balloon, the expanding universe does the same thing. I wanted to do an experiment, which I thought I could explain to my grandmother, and measuring the ultimate fate of the universe struck me as being a good experiment to do that. So when we started this experiment in 1994, we wanted to measure the ultimate fate of the universe by measuring how fast the universe was slowing down over time. That allowed us to see how much gravity there was in the universe.
For his standard candle, Professor Schmidt used Type 1a supernovae.
So Type 1a supernovae are explosions of white dwarf stars. So a white dwarf star is the thing that the center of our sun will become once it uses all of its nuclear fuel. So it turns out that the outer parts of the sun will blow off in about 5 billion years. The center of it will collapse down to something that is about the size of the Earth. And so that star is a ticking nuclear bomb if it can be made to grow to about 1.4 times the mass of our sun. So our sun will never do that. It doesn't have anyone to provide that mass. But if our sun was born as a binary star, then when our sun would become the white dwarf, this star could put material onto that, cause it to grow. At some point, the star ignites, and the whole thing in a period of a second goes kaboom, with the power of about 5 billion times what our sun puts out. When one of these things explode, they go from being something that's very, very faint. Over the course of about 20 days, they rise to 5 billion times the brightness of the sun, and then they slowly fade into oblivion. We can measure how bright they are to about 7%. And that is very precise. That's better than a light bulb. So we have these light bulbs, but these are light bulbs that are roughly 43 orders of magnitude brighter than a light bulb here on Earth. And so they are really, really bright. And we can see them all the way across the universe. So by measuring how bright these objects are, we can measure distance like Hubble tried to with stars, but we do it much, much more accurately. We were going to go through and measure a bunch of these exploding stars. We were going to measure how fast they were moving away from us, or their redshift as we call it. And we were going to put that together, and we were going to do Hubble's experiment nearby And then we're going to do it a long ways away. And of course, we're looking into the universe's past when we look a long ways away. So we're going to measure how fast the universe was expanding in the past and in the present and see how it's changing. And we're going to see how fast it was slowing down, then therefore weigh the universe, and that would tell us its ultimate fate. Is the universe going to expand forever, or is it going to slow down enough, reach a maximum size, and then collapse and go into the Gnab Gib? That's the Big Bang backwards. So at the end of 1997, Adam Riess, co-winner, one of the members of the team, was showing me the results he was getting, and they were strange. They were showing that the universe was not slowing down at all, it was speeding up. So, of course, we kind of figured that we had made a mistake, as one does. Initially, it wasn't too bad. I just figured out that'll be an easy mistake, we'll find it. And I have to say there was a context that the other team, the Supernova Cosmology Project, had put out a paper in 1997 saying that the universe was slowing down, and it was slowing down pretty quickly. And then when we get this measurement saying the universe is speeding up, you're saying, going, oh, geez, okay, we'll just find the mistake. But after a while, you're like, well, there's no mistake going away. And then you start getting perplexed because you're saying, God, we're going to have to go out and not only tell the world something crazy, the universe is speeding up, but that we are getting a completely different answer than the other team is getting something completely sensible. So I was concerned, definitely concerned. We think the solution to this is that the universe is made up of 73% of something that causes gravity to work in reverse, something Einstein called the cosmological constant and what we now call dark energy.
So how is the universe going to end? Well, it seems it's going to go a little something like this.